Hello and welcome back to the course on machine learning. Today we're talking about the multi-armed bandit problem. Don't you just love these names when they come up such cool names for machine learning algorithms and problems? Well, today we're indeed talking about this problem, and it is the example that we're going to be using in this whole section on reinforcement learning. We're going to be looking at different ways that we can solve the multi-armed bandit problem and comparing the results. But before we continue, I just wanted to mention that the multi-armed bandit problem is not the only problem that can be solved with reinforcement learning. Reinforcement learning is actually really cool. Reinforcement learning, for instance, is used to train robot dogs to walk. And I'll give you a quick example. For instance, once you've created a robot dog, you can implement an algorithm inside the robot dog which will tell it how to walk. You can tell it, all right, move your front right foot and then move your left back foot and then front left foot, right back foot, and so on. You can actually give the sequence of actions that it needs to take in order to accomplish a task, which is walking. Or you can implement a reinforcement learning algorithm which will train the dog to walk in a very interesting way. So basically what it will do is it will say, hey dog, here are all the actions you can take. You can move your legs like this, you can move your legs like that, and your goal is to make a step forward. Every time you make a step forward, you are given a reward. Every time you fall over, you're given a punishment, and a reward is basically a 1. In the algorithm, you don't actually have to give it a carrot or something to eat. You just give it a 1 in the algorithm, and a punishment is a 0. And basically every time it takes a step forward, it knows it's got a reward, and it will that's good for it. So it basically will try all these random sets of actions and see what they lead to. Every time it takes a step forward, it'll remember that those were good actions, and it'll try to repeat them more and more. And actually dogs like that can learn to walk. So you don't have to program an actual walking algorithm into it. It'll figure out the steps it needs to take on its own. I think that's really mind-blowing and really cool. But unfortunately, that is a topic more of on the side of artificial intelligence rather than just machine learning. And that is, that can be a whole course on its own. We're not going to delve into training robot dogs to walk inside this section. Inside this section, we are going to talk about the multi-armed bandit problem, which is a bit of a different application of this machine learning branch of reinforcement learning. And plus, of course, there's lots of other applications of reinforcement learning as well. So, moving on to our multi-armed bandit problem. So, first of all, what on earth is a multi-armed bandit, right? So the first thing that comes to mind is like a robber going into a bank and so on, and or somebody with a gun. But actually, a bandit, or a one-armed bandit. Let's start with let's simplify things. A one-armed bandit is a slot machine, right? It's one of these. And why is it called a one-armed bandit? Well, it's got a bit of a history there. Back in the day, they used to have this handle on the right, and you can still see that in movies, and maybe some places you can still find these slot machines where you actually have to pull the handle, because now they're all electronic and you just press a button, right? They're push slot machines, whereas back in the day you had to pull a lever to make it work, to like initiate the game. And so hence the arm, yeah? But why is it called a bandit? Well, because these machines, they would actually, this is one of the quickest way to lose your money in a casino. They would take, I think it was like a 50% chance that they would take away your money back in the day. So they would, of course, you would earn less than you're actually winning, and it was about a 50-50 chance whether you or not you actually make you get a win or you lose money. But then they put a bug into them. I read up a little bit online. They put a bug into them that people who were playing them were losing even faster than or even more frequently than 50%. So hence the name Bandit, because it was basically robbing you of your money, and one of the quickest ways to lose your money. Hence the that's why it's called the one-armed bandit. And what is the multi-armed bandit? Well, the multi-armed bandit problem is kind of the challenge that a person is faced when he comes up to a whole set of these machines, when he doesn't have just one, he has like 5 or 10. In our programming examples, we'll have example of 10, but we won't be talking specifically about these machines. Of course, this is the historic problem. We'll see that there are many other applications that, even though it's called the multi-armed bandit problem, it's actually used to solve many other problems as well. So basically here you're faced with a challenge. You've got 5 of these machines, right? And how do you actually play them to maximize your return from the number of games that you can actually play? So you decided you're going to play 100 times or 1,000 times, and you want to maximize your return. How do you figure out which ones of them to play in order to maximize your returns? Well, the problem, to describe the problem in more detail, we've got to mention that the assumption here is that each one of these machines has a distribution behind it. So there's a distribution of numbers out of which, or outcomes out of which, the machine picks results, right? So it has like each one of these machines has its own distribution, and it picks out a result. You pull the trigger and it just picks out randomly out of its distribution a result, an outcome, whether you win or whether you lose, and how much you win and how much you lose. Or basically you lose the same amount you just put in the coin. But basically it tells you whether you win or lose based on the distribution that's built into the machine. But the problem here is that you don't know these distributions, right? You don't know in advance what the distributions are, and they are assumed to be different for these machines. Sometimes they can be similar or the same in some of the machines, but by default they are different. And your goal is to figure out which of these distributions is the best one for you. So let's have a look. So there are these distributions, right? So for example, we've got these 5 machines, the 5 distributions, and as you can see right away, just by looking at this, which is the best machine right away? Obviously the one on the right, the orange one, is the best machine because it's got the best, it's the most left skewed because the tail's on the left. So it's got the most favorable outcomes, it's got the highest mean, median, and mode. And if you knew these distributions in advance, you would obviously just go to the 5th machine and you would bet on the 5th machine, just on the 5th machine all the time, because it's got the best distribution, right? So on average, you would get the best results. But you don't know that. You don't know that in advance, and your goal is to figure out. It's like a mind game. You know how there's all these movies about machine learning and really cool mathematics, and how they're using it. They're cool. A really good movie was Imitation Game, right? About Alan Turing and how he was solving the enigma and so on. But similar kind of concept. You don't know which one of these is the best. You got to figure it out. But at the same time, you are already spending your money doing this, right? You can't just, the longer you take to figure it out, there's a trade-off, right? The longer you take to figure it out, the more money you will probably spend on the wrong ones. And therefore you have to figure out very quickly. So there are these 2 factors that are in play: exploration and exploitation. So you need to explore the machines to find out which one of them is the best one. And at the same time, you need to, as soon as you can, already start exploiting these machines, exploiting your findings to make the maximum return. So basically, and there's another mathematical concept behind all of this, which is called regret. And regret is mathematically defined. And if you want to read more about this, there's a really good white paper on it. It's called Using Confidence Bounds for Exploitation and Exploration Trade-offs. And it is by Peter Auer, or Auer, from Graz University of Technology in Austria. Really like the white paper. It goes into a lot of detail. I didn't even read the whole thing, but the first couple of chapters are pretty good if you want to go into detail. But basically, regret is when is suffered when you're using a non-alternative, not optimal method, right? So the one on the right is the optimal, or the one on the right is the optimal machine. Whenever you're using the non-optimal machine, you have a regret which can be quantified as as the difference between the best outcome and the non-best outcome, and the all of those sums of the money that you put, like your opportunity cost of actually exploring the other machines. And so the longer you explore the non-optimal machines, the higher regret. But at the same time, if you don't explore for long enough, right? If you don't explore for long enough, then a suboptimal machine might appear as an optimal machine. So, for instance, this machine over here, right? So if we explore, but we don't spend enough time exploring, we might think that this is the best machine because it's got quite a good return, right? Close to this one, and we might start exploiting this one for the rest of the time. But then in reality, this one was the best one. So the goal is to find the best one and exploit the best one, but spend the least amount of time exploring all of them, right? And while you're exploring, you're still earning money, but not from the optimal machine, right? So that's the goal. That's the point of this whole exercise. And it's important to understand here that there is the best one. So that even though these machines, they have like jackpots sometimes and so on, but we are assuming that that these distributions are finite there, and out of them there's a best one that you are looking for. That's kind of the pre-emphasis or the whole assumption of this problem. If there are more complex options and versions of this problem, and again, check out some additional reading on that topic that's even more advanced. But what we're going to be using this for that's going to be sufficient. And why is that going to be sufficient for us? Because the most common modern application of this that we can think of, and the one that we are going to be exploring, is advertising. Voila. So let's have a look at some ads. This is going to be fun. So just a disclaimer, there's no affiliation with Coca-Cola. Examples are used just for educational purposes. All right, so let's have a look. We have, let's say Coca-Cola or some company wants to run a campaign, and it's going to be called Welcome to the Coke Side of Life campaign. And if you search for this campaign online, you'll see that they had hundreds of different ads that they came up with for this campaign. And here's one example of them, or these are just some images I pulled from Google, so maybe these are even drawn by people. But we're going to assume that these are legitimate ads that we're going to go into the campaign. And so we want to find out which is the best ad, which is the ad that works the best. So we've got options: number 1, number 2, number 3, number 4, and number 5. And so now our goal is to find out which ad works the best, or maximize our returns. But right now we don't know which ads work the best, right? So there is a distribution behind it, but that distribution will only become known after thousands and thousands and thousands of people look at these ads and click or not click on these ads. And this is actually going to be very similar to the example that we're going to be looking at, the example that Hadlan is going to be walking you through in the programming tutorials. In that example, we're actually going to have 10 ads, so even more. And so what can you do here? Well, one way to approach the problem is just run an A/B test, right? So take your 5 or 50 or 500 ads and run a huge A/B test or multiple A/B test, and wait until you have enough of a large enough sample, and then conclude which ad is the best, right? With certain confidence. But the problem with that is that you would spend a lot of time and money doing that, right? So an A/B test is pure exploration, right? You're not exploiting the best option. You are exploiting the best option, but to the same extent as you're exploiting the non-optimal options, right? So if we go by our previous distributions, if this is the best one, if you just run an A/B test, then you're uniformly distributing, or you're uniformly using these 5 options, and therefore as much as you're using this one, you're using all four of them. So basically all 5 of them. So basically you are exploiting it a bit, but unconsciously, right, in a random way, and therefore A/B tests are just for exploration. So the challenge is to find out which is the best one, but do it while you're to exploit the best one while you're exploring for it, right? So find out which one is the best one in the process of, hold on, find out which is the best one in the process of the actual launched campaign. So don't have two phases, do the A/B test and then use the best one, but actually find out the best one in the quickest way possible and start exploiting it along the way. So that's the challenge here, and that's what we're going to be solving. And that's the modern application of the multi-armed bandit problem. So hopefully you're excited about this. We've got 2 great algorithms coming up. Can't wait to get started. I look forward to seeing you in the next tutorial. And until then, enjoy machine learning.